Hello. So today I will be talking about Stirling's approximation. Stirling's approximation. All right. So what is Stirling's approximation? It is named after James Stirling, and he discovered an approximation for n factorial. N factorial. And this approximation is usually written one of two ways. The most common form is that the natural log of n factorial is approximately equal to n times the natural log of n minus n. Or it can also be written, instead of, if we want to actually approximate n factorial, will be approximately equal to square root of 2 pi n times n over e raised to the power of n. So these are the Stirling's approximation. The first one is most commonly used. All right, so let's see. Let's see if we can prove the first formula. All right, so log, the natural log of n factorial is equal to the natural log n factorial is n times n minus 1 times n minus 2 all the way times 2 times 1, all the way down to 1. And one can see that use the log rules, log of a times b, log of ab is equal to log of a plus log of b. And using that, we can rewrite this as the natural log of n plus the natural log of n minus 1 plus the natural log of n minus 2 plus the natural log all the way down to the natural log of 2 plus the natural log of 1. And okay, so we can, let's rewrite this more compactly as the summation from k is equal to 1 to n of k of the natural log of k. So we can rewrite this as a summation. And we can see that the summation can be approximated by an integral. And the integral will be the integral from 1 to n of the natural log of x dx. And so the summation can turn into an integral because if we take a look at the graph of the natural log of k, natural log of x, this is the natural log of x, and this one, right? So basically, this sum 1, 2, 3, 4, 5, 6, 7. So what this sum is doing is basically, we're basically calculating this area that I'm going to be shading in yellow over here. This is basically the area that we're going to be summing, and it can be approximated by the integral from 1 to n. And this approximation gets better as n gets larger. Okay, and then so let's see. to integrate, you can use integration by part to integrate the natural log. You can see that it will be equal to the natural log x, natural log of x minus x from 1 to n, which will be approximately equal to x n natural log of n minus n. And this is basically Stirling's approximation. First one, so the natural log of n factorial is approximately equal to n log n minus n. Okay. And one can use the Euler-Maclaurin formula to get an error term, and you can see that it is of the order of the natural log of n. And so basically, Stirling's approximation is like an approximation of n factorial, right? And it works just like any other approximation. It's not precise, but it's good enough for any of our uses. For example, to approximate pi, we have the common ones at 22/7 and 3.14. And these are basically a common approximation of pi. Actually, a really good one is a really good approximation of pi is 355 divided by 113. And if I take out my calculator and calculate that value, let me see, 355 divided by 113, that would equal to 3.1415929 ... Pi is actually equal to 3.14159265358, etc. And so we can see that it's actually a really good approximation. And just like Stirling formula, it's actually a good approximation of n factorial, of the log of n factorial, actually. And other approximations, like you to approximate the roots of a number, we can use the slope of the tangent line. Let's say we want to approximate, I don't know, the square root of 7. Then we can use f of x is equal to x to the 1/2, and the closest square to 7 will be 9. And so we can use the square root of x and 9 3, and we can use this tangent line. I'll do the tangent line to complete that. We can use the slope of this tangent line to approximate the square root of 7. Yeah, and so basically we can find that f prime of 7 will be 1 over f prime of 9 will be 1 over 2 times the square root of 9, which is 1/6. And so y minus 3 will be equal to 1/6 times x minus 9, x minus 7. So since x will be 9, 9 minus 7 is 2. Actually, x minus 9. 7 minus 9 is -2. Negative times 6 is a third. So negative a third. 3 minus a third is 22 and 2/3, which will be 2.67 will be my approximation of the square root of 7. And if we use our calculator, 7 raised to the power of 1/2 is approximately 2.65. So this is a good approximation of the square root of 7. Also, we have a Taylor series, right? Taylor series are basically approximation, polynomial approximation of functions centered at any arbitrary point, and the Maclaurin series, which are Taylor series centered around 0. And so using the Taylor polynomials, we can get the common approximations that we use in physics, like a small angle approximation. Sine of x is equal to the tangent of x is equal to x, and a cosine of x is equal to 1 minus x squared on 2. So these are common polynomial approximation of the trigonometric function that we use in physics known as the small angle approximation. We have to have Newton's method, which can be used to approximate the roots of function. And so this Stirling formula is also an approximation of the log of n factorial, or actually the n factorial if we use the more precise formula. What are some practical applications of this? Well, in computer science, there are sorting algorithms that are called comparison sort. And so basically, in comparison sort, the minimum number of comparison is on the order of log base 2 of n factorial, the minimum number of sorting. And so we can use Stirling approximation. And we can find that actually n times log base 2 of n over e plus log base 2 of the square root of 2 pi n, if we use the more accurate version of Stirling formula. So that would be approximately the order of our the time complexity of our algorithm. And also in physics, we have a famous physicist, Ludwig Boltzmann, who defined the entropy of a system to be k sub b, which is the Boltzmann constant, which is a very small number, but we don't have to worry about that, times the natural log of omega. And that's basically a very famous formula calculating the entropy of a system, and omega is the number of states, the number of microstates of the system. And for simplicity's sake, I just assume k sub b to be 1. Then we want to find the entropy of a deck of cards. A deck of cards, a standard deck has 52 cards. The number of microstates will be 52 times 51 times 50, on and on to 2 times 1, which will be 52 factorial. And we would just calculate the entropy. I just assume k to be 1 for simplicity. So h will be equal to, actually, let's just say h over k sub b will be equal to the natural log of 52 factorial. And without Stirling's approximation, we have to calculate 52 factorial, which is a gigantic number, and take the natural log of that. But with Stirling's approximation, we can approximate it to be 52 times the natural log of 52 minus 52. And if we calculate that, we get 52 minus natural log of 52 times natural log of 52 minus 52. And we get 153.5. And if we actually calculate the actual value of the natural log of 52 factorial, where is it? Factorial of the factorial, we get 156.4. So we can see that Stirling's approximation works really well. So yeah, that's basically Stirling's approximation.